The Permo-Triassic mass extinction event is probably the greatest catastrophe the biosphere faced since complex life evolved about 600 million years ago. A cascading series of events, probably triggered by extensive volcanic activity in Siberia, that would see the development of a runaway global warming and extinction across vast swathes of the biosphere. Roughly 90%, with sometimes estimates as high as 96% of species going to extinction in the geological snap of the fingers. We have already charted those difficult times of this series, but what about the aftermath? It's easy to get distracted by the fireworks of the big event and forget about the world that would follow the disaster. Doug Irwin of the Smithsonian's Department of Paleobiology makes an interesting point. Does the cause of these extinction events really matter? Perhaps generating a general theory based on the causes of mass extinctions is, as he put it, misplaced. Perhaps we should be more focused on how ecosystems fell apart, as this may have great implications for biodiversity losses occurring today. Although the trigger of an ecosystem collapse may vary, perhaps they all fall apart in a similar way. To gain insight into this, let's look at the world of the early Triassic just after the end Permian bomb was dropped and see if we can chart the biosphere's recovery. So in this episode, let's ask, what was the world like in the early Triassic? What was left of life following the greatest of all extinctions? What was driving the impoverished early Triassic, and why did it last so long? When did the Earth start to recover? And what was there that could possibly give us even more doom at the end of the Triassic? During the early Triassic, our planet would have looked very, very different. A giant landmass, Pangaea, dominated one side of the planet, surrounded by the vast Panthalassic Ocean. The early Triassic climate was harsh on Pangaea. Hot, arid deserts covered most of the interior of the supercontinent. Evidence for this is found in many of the red desert sandstones we find that occasionally contain evidence of fossil sand dunes. Further proxies of hot conditions come from evaporite deposits. These can form by the evaporation of inland bodies of water and the precipitation of various salts as the water continues to concentrate and dwindle. You can see some modern examples here in Deep Spring Lake, California, and along the margins of the Dead Sea in Israel. It is possible that this was the hottest and most arid time in over 500 million years. In fact, there is likely no ice at the poles. Indeed, it is possible that the poles might have been relatively temperate places, where forests and a more diverse biota of plants, fungi and animals could survive. It is the inverse of what we have today, as in the early Triassic, the temperate polar regions were more habitable than the equatorial regions. Analysis of oxygen isotopes taken from conodonts, the tooth-like mouthparts of an early chordate, paint a disturbing picture of the temperature change during the early Triassic. Research in equatorial deposits from southern China, spanning the period of the extinction at the end of the Permian and continuing into the early Triassic, show a rapid warming in the oceans from 21 to 36 degrees centigrade. The warming peaks at around 252.1 million years ago, the end of the Permian. There is a cooling following this, and then a second rise in temperatures occurring around 250.7 million years ago, a period of the early Triassic called the early Olenikian, when temperatures in the water column rose again to about 38 degrees Celsius, and perhaps even exceeded 40 degrees Celsius at the surface. At such marine surface temperatures, organisms such as corals cannot survive. The life forms that would limp across the Permo-Triassic boundary would inherit a truly impoverished world. In general, they are referred to as disaster taxa. One of the poster kids for these disaster taxa is a strange shovel-faced animal called Lystrosaurus. Lystrosaurus was a member of a group of reptiles called the Dicynodonts, that means two dog-like teeth, that are named for their paired tusks. They belong to a wider family of reptiles called the therapsids, or colloquially, the mammal-like reptiles, that are important in our evolution of our group, the mammals. Although it evolved during the Permian, Lystrosaurus was most abundant during the early Triassic between 251 to 247 million years ago, where it made up over 90% of the terrestrial vertebrate species on Earth. The animal probably cropped vegetation on the surface, but may have been able to dig for material if times got tough with those powerful front limbs. It is this adaptability that might have allowed Lystrosaurus to struggle through the difficult early Triassic times. On the whole, it would be the generalists like this stubby reptile and not the specialists that would make it through the troubled early Triassic period. And what of the plant life that Lystrosaurus may have dined upon? Forests were not common in the desert planet, and where plants were present, they would be dominated by smaller herbaceous forms like Neocalmites, horsetails, and the lycopod Pleuramia. This may also explain why we see that transition in the early Triassic from the meandering river systems in the Permian with banks stabilised by plants to the more chaotic braided systems that followed afterwards. This is a signal that plant communities have retreated, and along with them, their ability to stabilise the banks of river channels. At the same time, as we discussed in the previous lecture, there is an increased delivery of sediment to the oceans that contains soil-derived biomarkers. Soils were being stripped and washed away. The reduction in flora may also explain the coal gap in the early Triassic that suggests a lack of wetland plant communities and peat swamps. Coals would not appear in equatorial regions till about 15 million years after the Permo-Triassic extinction. Dr. Conrad Lambandera is a paleoecologist in the Department of Paleobiology with a particular interest in plant-insect interactions over geological time. His research shows the dramatic changes that occurred in insect faunas across the extinction boundary, an event that he describes as being one of the most profound in the evolutionary history of insects. As you can see from this illustration in a paper Conrad published in 2005, the mother of all extinctions, as his colleague Doug Irwin calls it, divides the history of insects into two evolutionary faunas. Many Paleozoic lineages become extinct. In fact, we lose most insect species. This is a linked plant-insect ecological event that would have profound effects on the associations between plants and insects. For example, pre-extinction Permian herbivorous insects favoured consumption of plants from the outside, while post-extinction Triassic species consumed their plant host from within. You can see that on these drawings made by Conrad of fossils from South Africa. Of course, the situation on land was just half of the story. Life in the oceans had been decimated too. The oceans, just like the continents, were dominated by high abundance but low diversity faunas. The rich invertebrate assemblages of the pre-extinction Permian world were reduced to just a few species, such as the brachipod lingula and the bivalve claria, classic disaster taxa found in the oceans at this time. This is also a world with no corals. In fact, just like the coal gap on land, there is a similar reef gap in the oceans, with coral reefs not returning to the planet until about 9 million years after the start of the Triassic period. The only reefal structures at this time would be stromatolites, those columns of cemented sediment created by laminated mats of microbes. Stromatolites have been pretty well absent from most environments since the Ordovician, 190 million years earlier, but probably make an appearance in the Triassic due to the decimation of all the grazing creatures that would usually keep them in check. There is also a geographical pattern to the impoverishment of the taxa during the early Triassic in both the marine and terrestrial realms. This pattern is particularly noticeable during that peak temperature rise during the Olenekian. At this time, a disturbing gap in fossils occurs at the equator. It appears that the equator had become a dead zone. This is not due to a lack of the right age rocks or because of conditions that were not conducive to fossilization. Simply put, most life was just absent at low latitudes. In the oceans, fish, marine reptiles and corals are missing. Life in these zones tends to be invertebrates of limited diversity and, of course, stromatolites. The situation is the same on land. The majority of the impoverished fauna that survived the extinction at the end of the Permian retreated towards the more hospitable poles. Contrast that with the distribution of life today, where a latitudinal band north and south of the equator shows overwhelmingly the greatest biodiversity on the planet, a biodiversity that typically decreases as you move towards the poles. By contrast, life on planet Triassic had not only been impoverished, but that pattern of remaining diversity had flipped. Another feature of many, but not all of the taxa found during these times is their size. They're generally very small. This is thought to be related to a phenomenon called the Lilliput effect, named for the tiny people Gulliver visited in his travels. The Lilliput effect is seen to occur after crises in the biosphere and manifests in smaller adult sizes and also in an increased juvenile mortality rate. Together, these demographic features result in a fossil record characterized by smaller individuals. This probably also explains why the trace fossils only record the presence of small organisms, since there were no large species that were burrowing very deeply at this time. It would appear that the increase in lethal temperatures during the early Triassic, especially at equatorial latitudes, is pushing organisms beyond their thermal tolerances. For many plants, that threshold temperature is about 35 degrees centigrade, with few being able to survive above 40 degrees centigrade. For animals, temperatures over 45 degrees centigrade are very serious physiologically, with marine animals having a much reduced tolerance to rising temperatures. About 35 degrees centigrade is their limit. This is due to increased risk of hypoxemia, the lack of oxygen in the blood, as rising temperature will reduce the amount of dissolved oxygen available in water. This also explains why active marine creatures like fish and cephalopods are absent or rare at the equator. The more active you are, the more active your metabolism, and the more active your metabolism, the greater your demand for oxygen. With reduced potential prey, the number of marine reptiles would be reduced too. So it would appear that elevated surface temperatures were driving this period of extreme low biodiversity. But isn't that just what we should expect? After all, we have just come through the largest mass extinction ever at the end of the Permian. Surely it would take time for the Earth to cool down and recover. That's true, but in most extinctions, the biosphere is well on the way to recovery within hundreds of thousands of years. For the Permian extinction, however, things were still pretty awful up to 5 to 7 million years into the Triassic. In fact, the only reason why another mass extinction is not registered at this time is that there was pretty much not much life left to go into extinction. It is important to note, though, that it was not just rising temperatures that were the problems. Increased temperature had caused a whole cascade of related problems during the Permian extinction, problems that persisted well into the Triassic. These difficulties included reduced oxygen conditions, what we call dysoxic or anoxic, in various parts of the oceans, and the possibility of associated rises in hydrogen sulfide due to the proliferation of those certain sulfur-loving bacteria that like to live in those oxygen-poor conditions. Increases in carbon dioxide levels would also mean more dissolved carbon dioxide in oceans, making seawater acidic. This would ensure that creatures like the corals that secrete thick carbonate shells and skeletons would have a long wait before they could make their comeback. Bivalves from this period, like Claria, that still produce calcium carbonate hard parts, could only manage to secrete shells that were relatively thin. Dr. Richard Bambach, a research associate in the Department of Paleobiology, was an author in a 2007 paper published in Earth and Planetary Science Letters. This paper examined the selective nature that the extinction had on marine invertebrates, and it concluded that this was best explained, but not exclusively explained, by elevated levels of carbon dioxide or hypercapnia. He also notes that early Triassic land vertebrates display features such as respiratory turbinals, structures that increase the surface area over which air is processed in preparation for the lungs, and also display burrowing behaviours that may have helped them survive in a hot, carbon dioxide poisoned world. So what was maintaining these environmental conditions way beyond the Permo-Triassic? At the moment, it's still unclear. It is possible that the Siberian traps, one proposed smoking gun for the end Permian extinction, was still active and releasing carbon dioxide. This delay may be responsible for the continued warming that we see at the end of the Orlanician. Perhaps this warming also helped destabilise more methane hydrates, further warming the planet. At the moment, though, evidence for this or another source of warming has yet to be found. Eventually, though, through the Middle and Late Triassic, in both the continental and marine realms, numbers and diversity of lineages started to increase significantly. In addition, there is evidence of more complex ecological associations developing too. For example, by the time we see the Middle Triassic, we start to see long-term reef development initiated again. The principal reef builders of the pre-Permian extinction events, the rugose and tabulate corals, were gone though, as were many of the invertebrates and vertebrates associated with them. Although there is evidence of some minor reef formation about 1.5 million years after the Permo-Triassic, mostly by sponges and serpulids, those are worms that secrete tubes out of calcium carbonate, it is not really until around 5 million years after the extinction that stony corals really start to make a comeback. It is during the Middle Triassic that we see the first scleractinian corals at about 240 million years ago, the corals that are the main reef-forming metazoans today. Another example comes from terrestrial plant-insect interactions. There is a quantum leap in plant-insect activity commencing during the Middle Triassic and expanding especially throughout the Late Triassic. Dr. Conrad Labandera has been investigating how insects were initiating these associations with plants starting around this time. For example, these are the scars and eggs left by a female insect as she used her sword-like ovipositor to lay eggs in a fossil plant stem from the Middle to Late Triassic of Kyrgyzstan. Conrad has also found a whole spectrum of new plant-insect, plant-mite and fungal associations from the Late Triassic of the Karoo Basin in South Africa. For example, insects chewing holes through leaves, munching along leaf margins, and mining within leaf tissues. Not only does this show that plant and insect biodiversity was improving, but also that innovative interactions between different life forms were starting to increase and food webs were becoming more complex, an important engine in the evolution of new species and increasing biodiversity. The Middle Triassic also sees the spread of mollusks like bivalves, clams and gastropods, snails. Prior to the Permian extinction, the shells you would have commonly found washed up on a beach would likely have been brachiopods, sometimes called lamp shells. Brachiopods may superficially resemble clams, but they belong to a very different group of animals than the mollusks. They have a lophophore, that's a ring of ciliated tentacles to capture material suspended in the water column. You can see a lophophore here on a related animal called a bryozoan. By the time we get into the Middle Triassic, the bivalves are recovering and diversifying, but brachiopods, although they're still with us today, will never dominate the ocean floor the way they did in the Paleozoic. The seashells of the Mesozoic and the Cenozoic would be dominated by mollusks. The Middle Triassic to early Jurassic interval would also see the expansion of terrestrial and freshwater vertebrate faunas. An early example is in the rise of archosaurs, which by the mid-Triassic had started to replace the mammal-like therapsid reptiles such as Lystrosaurus. Archosaurs included Raucisuchia. These were scary animals resembling a crocodile on long legs that ranged in size from about 4 to 6 meters. But another archosaur had emerged. Not yet quite as imposing and impressive as they would ultimately become, but showing great signs of promise. The dinosaurs had arrived. Now, dinosaurs did not dominate the Triassic, but were a part of a rapidly diversifying vertebrate fauna. Probably one of the best known of these Triassic dinosaurs is Coelophysis, a slender bipedal carnivore about 3 meters long. Coelophysis is very common in the southwestern United States and has been found in other regions of the Triassic world too. It was probably an agile runner, with its forward-facing eyes providing stereoscopic vision with good depth perception. 1,000 specimens were discovered at the Whitaker Quarry in Ghost Ranch, New Mexico. This has led to speculation that Coelophysis may have roamed the Triassic in large flocks. This is difficult to prove, however, as it is also possible that these creatures had gathered at this location to drink before they were overcome by a flash flood event. Nevertheless, it does show what a common and successful creature this little dinosaur was. The archosaurs would also move the vertebrates into the atmosphere during the later Triassic. Early gliding creatures like Cherovipteryx are found in the mid-Triassic of Central Asia, but it was the pterosaurs in the late Triassic like Eudimorphodon that would develop truly powered flapping flight. And, in a way, it is from this burst of diversification following the Permian extinction and the barren, hot earth of the early Triassic that our story would start. It is likely that some of the earliest mammals had evolved by the late Triassic from some of those mammal-like therapsid reptiles that had been so common in the Permian and early Triassic. It's kind of difficult to distinguish between the last of the therapsids that were starting to look increasingly like mammals and true mammals, but late Triassic animals like Megazostrodon are certainly starting to look very mammalian. As encouraging as all this explosion of life in the latter Triassic may sound though, there will be another setback before the flourishing of the world we are all familiar with from movies like Jurassic Park. For at the end of the Triassic, about 201.3 million years ago, it would appear that the wheels are coming off the wagon again, this time in an event called the Triassic-Jurassic mass extinction, extinction number 4 in the big 5 mass extinctions. In the oceans, the conodonts that had been such an important part of the Paleozoic fauna would be extinguished. Reef systems would suffer once again, and ammonites, brachiopods and bivalves all would suffer significant extinctions. In total, it is estimated that 22% of all marine families, 53% of genera, and an estimated 76 to 84% of all species may have been driven into extinction. On land, many plant groups were extinguished, as Dr. Peter Wagner from the Department of Paleobiology has noted in his studies of the floras of Greenland. The plants Peter was studying do not show a simple decrease in taxa, but also demonstrate decreases in the number of common taxa, a change that was attributed to increasing CO2 and associated global warming. For tetrapods on land, the story is pretty grim too. Many of the archosaurs and remaining therapsids and many large amphibians become extinct. So what went wrong this time? In truth, the Jurassic-Jurassic extinction is a difficult extinction to tie down, as was formerly the case with the Permo-Triassic extinction, because there are so few sections of sediments that cover the extinction interval. In fact, some paleobiologists, as we will see later, suggest in fact that no extinction took place. It is possible that falling sea levels could have caused the crisis. This would have reduced the area of shallow warm seas and restricted the spread of reefs, but the reasons for these sea level changes are uncertain at the moment. We do know that something very significant was happening in the Earth system at this time though. Pangaea, a familiar geographical feature of the Triassic period, was really starting to fragment with a series of rifts opening between the Americas and Africa and Europe. Evidence of this rifting can be seen in sediments, mostly late Triassic to early Jurassic in age, located in eastern North America called the Newark Supergroup. These sediments are very thick, around 6 kilometers at Newark in New Jersey, and consist of a package of mostly terrestrial sediments deposited in fault-created downdrop valleys that we call half-grabens. Many of these sediments were deposited in lakes, that developed along the line of the rift. For a modern rift analogy, think of the East African rift system today. This is a rift that is currently developing under East Africa that may at some point see the development of a new ocean floor and the separation of this part of Africa from the mainland. The East African rift is also associated with volcanic activity, for example, Mount Kilimanjaro and Mount Nyiragongo. In the same way, the rift that would eventually widen to form the Atlantic Ocean was also a centre of igneous activity. Dramatic evidence of all this activity can be seen if you take a boat down the Hudson River. This large cliff is the New Jersey Palisades Sill, originally a basaltic magma that was injected into the crust. The Palisades Sill is just one example of the huge volumes of hot magma that were being intruded into this area of the Pangaean crust at the end of the Triassic period about 200 million years ago. This igneous activity was all part of what is known as the Central Atlantic Magmatic Province, or CAMP. Not only were intrusive bodies of igneous rock that never got to the surface like the Palisades Sill being produced, but also vast outpourings of lava found today in Northwest Africa, Southwest Europe, as well as North America. The CAMP eruptions are concurrent with the extinction, producing a volume of magma that would cover an area of about 11 million square kilometres. The thickest deposits of lava today are found in the high Atlas Mountains of Morocco, where flows can reach as much as 300 metres thick. The CAMP eruptions are the first murmurings of the splitting apart of Pangaea. Research by Sam Bowring and Robert Schrock of MIT have radiometrically dated these deposits and have concluded that all this material was erupted in a fury of activity lasting incredibly only 40,000 years, a rapid shock to the Earth system. Such vast volcanic activity could have caused the effects we have previously described for the Permo-Triassic extinction: global cooling due to the release of sulfur dioxide and aerosols, followed by intense warming as carbon dioxide levels started to rise in the atmosphere. Such warming may have also caused the destabilization and dissociation of gas hydrates in sediments on the ocean floor, therefore releasing methane and causing even more global warming. A team of scientists, including researchers at University of Southampton in the United Kingdom and the Geological Survey of Canada, have found evidence from sediments now exposed on Haida Gwaii, the Queen Charlotte Islands, of this warming. At the time of deposition, these islands were located in the northeastern Panthalastic Ocean. They found chemical fossils of photosynthesizing brown pigmented green sulfur bacteria. Such bacteria only live in anoxic conditions, producing hydrogen sulfide as a waste product of their respiration. This demonstrates that in this area at least, the upper ocean suffered severe oxygen depletion and hydrogen sulfide poisoning. The global warming caused by the CAMP carbon dioxide release may have acted as the trigger that would slow down oceanic circulation, restricting the ventilation of the oceans with oxygen and allowing these bacteria to thrive. The oceans, just as they had at the end of the Permian, may have become sick again. There have been alternate triggers suggested for the extinction. For example, the Eye of Quebec in Canada is a pronounced geomorphic structure occupied today by Lake Manicouagan. This is actually the remains of an ancient impact crater, the sixth largest on Earth. It formed when a 5-kilometre diameter asteroid impacted this area during the late Triassic. The crater was originally about 100 kilometres wide, but has now been eroded down to where it is only at about 72 kilometres wide. At its central point is Mount Babel. Mount Babel is interpreted as being formed due to the post-impact uplift of the ground as it rebounded after the asteroid hit. Could this be the smoking gun of the end Triassic extinction event? Unfortunately for the impact hypothesis, recent dating of the Manicouagan crater places it some 12 million years before the extinction occurred. So that leaves us with CAMP and possibly sea level changes as currently the best explanation for the Triassic-Jurassic extinction. However, There has been suggestions that the decrease in diversity was caused more by a decrease in speciation than an increase in extinction. This decrease in speciation is a kind of slowing down of the engine of biodiversity, with normal rates of extinction not being met by a similar rate of new species evolving. As you can see from this figure in Conrad Lambandera's 2005 paper about family-level insect extinction, there is no significant downturn across the proposed extinction boundary. Whatever this event actually represents, the world following the Triassic would see a glorious new ecosystem dawn. Dr. Bambach, in a paper that he co-authored with Andrew Bush of the University of Connecticut, notes that from the Jurassic there was, as he puts it, a sustained taxonomic radiation. The Jurassic is sometimes called the golden age of the dinosaurs, but to many paleontologists it was the golden age of life, a life that had been proven through earlier, very trying times in Earth's history.